Everybody, this is Mr. Bortnick for AP Calculus AB. We are continuing our trigonometry overview this week, focusing on lesson 2, which are reciprocal and inverse trig functions. I am assuming that you've watched the first lesson in this series, so please, if you have not, go back and watch the videos about how we construct the unit circle and use the unit circle to find sine and cosine and tangent. But enjoy.
All right, for lesson 2, trigonometric relationships using the unit circle, I am assuming that you've watched the first video where we constructed the unit circle from scratch, talked about how to find degrees and radians and how to convert from those, and then how to use the unit circle to find sine, cosine, and tangent. In today's lesson, for lesson 2, we're going to be talking about what the reciprocal trigonometric functions are, using the unit circle to solve problems like sine of x is equal to 1, these functions called arcsine, arccosine, and arctangent, how to use your calculator to solve basic trigonometric problems, and then the Pythagorean identities. So we're going to start with the reciprocal trigonometric functions. Our definition with triangles, we're going to go back to sort of our right triangles, what we know from geometry and from a couple of years ago, is that if we've got a right triangle, so for example, this triangle right here, and we've got an angle, we know that in general for a right triangle, that the longest side is what's called the hypotenuse. We know that the side that's next to the angle is adjacent. Adjacent means next to, and then opposite side is the one that's not touching the angle itself. We know from our acronym from geometry that there's this acronym called SOHCAHTOA, that helps us remember the three basic trig functions for a right triangle, specifically that sine of theta is equal to the opposite over the hypotenuse, that cosine of theta is equal to the adjacent over the hypotenuse, and that tangent of theta is equal to the opposite over the adjacent. So these are the three basic trig functions, and these are the ones that are most commonly used. However, they are not the only trig functions that there are. In fact, there are three others which are referred to the reciprocal trig functions. That sort of round out our six basic trig functions. And so they are intentionally called the reciprocal trig functions because by definition, they are reciprocals of our three basic ones. So for example, the very first one which we're going to talk about is called cosecant. Cosecant is the first one, not to be mixed up with cosine, right? Those are, I guess it's probably useful to write these as well, right? This is our sine, this is cosine, this is tangent. So cosecant sort of looks like, almost like cosine, but they're different in terms of name. And it's defined as the reciprocal of the sine function. So we don't want to call it COS because that would be confusing if it was cosine. Cosecant, the abbreviation for that is CSC. So cosecant of theta, it's defined as the reciprocal of sine of theta. So if we took the sine function and we took whatever that was and we took the reciprocal of it, we would have cosecant. And so what is that in this case? Well, if sine is opposite over hypotenuse, the reciprocal of that would actually be the hypotenuse over the opposite. So notice it uses the same things in its ratio, it's just flipped over. Our second trig function, reciprocal trig function, is what's called secant, the secant function. And that one has the abbreviation of SEC, so secant of theta. And we define secant of theta as the reciprocal of the cosine function. So it's going to be 1 over the cosine function for that angle. And similarly, if we know that cosine of theta is the adjacent over the hypotenuse in a right triangle, we can just take the reciprocal of that fraction and make that the hypotenuse over the adjacent to find the secant function. Our last of our reciprocal trig functions is what's referred to as cotangent. cotangent, and it is defined as the reciprocal of tangent function, right? Tangent, cotangent, those sort of make sense, those match up. The way that we remember that and the abbreviation we use for that is COT, cotangent of theta, and that's going to be equal to the reciprocal of tan, the tangent of theta. And since tangent was opposite over adjacent, that means that cotangent as the reciprocal is adjacent over the opposite. So these are what I'm going to refer to as new. I'm not 100% sure if you've seen these before. You might have seen them back in geometry class, or you might have talked about these briefly with Mr. Insulaco in your Honors Algebra 2 class last year. But if not, these sort of round out our 6 most basic trig functions. There are the 3 sine, cosine, and tangent, and then these 3 reciprocal trig functions. Now, we can find these on any sort of given right triangle, just depending upon what our angle is and what those side lengths are. For example, we could just draw a basic like 3, 4, 5 triangle like this. So 3, 4, 5, and let's say our angle is right here. If that was the case, I wanted to find my 6 trig functions, like what we've got right here. We could say that sine of theta, well, first off, we'd want to label what each of these sides are. This would be my hypotenuse, this would be my adjacent, this would be my opposite. So sine of theta in this case, it would be the opposite over the hypotenuse. So that's going to be 3 over 5 would be what sine of theta is equal to. Cosine of theta in this problem would be the adjacent over hypotenuse. That would be 4 over 5. Tangent of theta would be the opposite over adjacent. That's 3 over 4. If we wanted to do cosecant of theta, we know that it's the reciprocal of the sine function. So if sine was 3 over 5, it's going to actually be 5 over 3 for cosecant. Secant of theta is the reciprocal of the cosine function, which was 4 over 5. So that reciprocal would be 5 over 4. And then cotangent is the reciprocal of tan, which was 3 over 4. So this is going to become 4 over 3. So that is just sort of a brief, very brief introduction to what those reciprocal trig functions are, and to see some examples of that with respect to a triangle. But we know that we're really focusing a lot on the unit circle, so I want to talk about how this works with our unit circle as well. We talked about in our previous lesson how to use that unit circle to find sine of a given angle, cosine of a given angle, and the tangent of a given angle. Specifically, we know that the sine, if we want that, is the y value of the coordinate that's there. The cosine is the x value. Tangent, because tangent is sine over cosine, that's going to be the y value divided by the x value. So if we know for each of these coordinates, right, these are x and y values that we're talking about here, all of those coordinates going around the unit circle, any of these, if we know that for each of these values, we could do a similar thing for our reciprocal trig functions. Right? We know that cosecant is the reciprocal of sine, so that's going to be the reciprocal of y, so that's going to be 1 over y. Secant is our reciprocal of cosine, and that was x, so it's going to be just 1 over x for that. And cotangent, the reciprocal of our tangent function, this was x over y. If we take that reciprocal, the fraction is going to flip. That's going to be x over y. Or sorry, the original was y over x. This is going to become x over y for that. Let's do an example where we're doing this with a specific number. So let's say, for example, that we're going to find all of these for when the angle is equal to pi over... no, let's do like pi over 3. So let's do pi over 3. So if I do sine of pi over 3. Again, what I'm going to look at on my unit circles, I'm looking here at pi over 3, and I'm looking at these coordinates here, right? We've got our x, and then we've got our y. We know the sine is going to be equal to whatever that y value is, and so this is going to be equal to root 3 over 2 from that unit circle. If I were to ask the cosine of pi over 3, that's going to be equal to the x value, which is 1/2. if I want to do the tan of pi over 3, that's going to be equal to the sine divided by the cosine. So in this case, that's going to be root 3 over 2 divided by 1/2. And how would we simplify that? Well, those 2's would cancel each other out. So this is the square root of 3 divided by 1, which is just going to be equal to the square root of 3. So that's what tan of pi over 3 would be. But if we want to find the reciprocal trig functions, well, cosecant of our pi over 3 is going to be the reciprocal of sine. So now that I know that sine is root 3 over 2, well, then the reciprocal of that would be 2 over root 3. So cosecant of pi over 3 would be 2 over root 3. However, as we know, we can't leave square roots in the denominator. That's not simplified all the way. So if I were to simplify that, I would multiply by root 3 in the numerator and denominator, and that would be equal to 2 root 3 over 3 for that value. For secant of pi over 3, we know that it's the reciprocal of our cosine function, which was 1/2. The reciprocal of 1/2, if we flip that fraction, is just 2, or 2 over 1. That's going to be our cosecant for that one. For cotangent of pi over 3, we already said that the tangent was root 3, and we know that cotangent is the reciprocal of tan. So we know that this is going to actually equal 1 over the square root of 3. But again, we know that we also cannot leave square roots in the denominator, so we multiply by root 3 over root 3 to give us the square root of 3 over 3. For that cotangent, we've got the secant, we've got the cosecant, we've got all of these for the angle of pi over 3. Now again, I can do this exact same idea if I needed to find any of these 6 trig functions. Sine, cosine, tangent, cosecant, secant, cotangent. I can do that for any angle on this unit circle. And so the unit circle is a fantastic tool because it helps me find these exact values, right? I can find these exact values of what these trig functions are equal to if I know how to use my unit circle. So that is a fantastic tool. Great. Let's move on to using the unit circle to solve equations like sine of x is equal to 1. So, as we said before, we know that each coordinate that's on here, our x comma y, is sort of written in the form of the cosine of whatever that angle is, comma the sine of whatever that angle is. And so that is true for each of these as we go around, which is super nice. But notice here in this first problem, they have an equation, sine of x is equal to 1, and they're not telling us what the angle is. So in this case, what this problem is asking us here is we're saying, well, what is this angle? What is this angle? What does the angle need to be if the sine of some angle is going to be equal to 1? Now, for us, we know that because this is sine, we are really looking for y values, where the y value is 1 going around here. And we can sort of see that there's only one place where that occurs. That appears to be right here up at this point, where the y value is 1, and that is when the theta is equal to pi over 2. So this would be true when x is equal to pi over 2 if we're being limited to the domain of just our unit circle. The reason why I bring that up is because we know from the last lesson that we know that it's possible to go both forward around the unit circle in positive direction, or you can go in the negative direction around the unit circle, ending up at these same values, what we called coterminal angles, right? So another example of a solution to this, right? We said pi over 2 is the only one where we see y on this, but all we really see here for our domain is from 0 to 2 pi, right? Those are the only radian values that we see on the unit circle, but we know intuitively and from what we talked about that we can go around this unit circle as many times as I want. So an example of another answer where the sine would be equal to 1 is I could, for example, do this, even though this doesn't really ask for it. I could take that pi over 2 that I had, and if I wanted to generate another solution to this, I could actually add 2 pi to it. Or I could subtract 2 pi to it, but I'm going to add 2 pi to it. Why 2 pi? Well, 2 pi, remember, would be the representing me going around a whole circle, and the whole circle itself is 2 pi radians. So I'm essentially saying pi over 2 is an answer, but if I went around another circle, then I would have the same answer again. So in this case, this is the same thing as pi over 2 plus, what's that, 4 pi over 2? And so a different answer would be 5 pi over 2, which if you wanted to check in your calculator, if you wanted to plug into your calculator and check, we could see that sine of pi over 2 is equal to 1. We should also see that sine of 5 pi over 2 is equal to 1. So this is actually an interesting question, because if they don't tell us the domain, if they don't tell us that we want just the answers on the unit circle, we could actually have an infinite amount of answers. Right? These are just two answers, but I could keep adding 2 pi over and over and over again. I could go into negative direction and subtract 2 pi to get different values. All I would need to do is keep going around the circle a certain number of times, and I would generate more answers to this. But if we're thinking about just the unit circle, this would be totally acceptable for our answer, just x is equal to pi over 2. Cool. What about this one? We've got the 2 cosine of x is equal to root 3. In this case, we're trying to solve for x, and so in this case we would really just want to divide by 2 on both sides, and so we would see that cosine of x is equal to the square root of 3 over 2. So cosine of x is equal to square root of 3 over 2. Now, one thing to notice about this, if we're thinking about it, root 3 over 2, we're looking again for an x value, right? Because cosine is our x values. If I'm looking for the square root of 3 over 2, I do see an answer that's right here, and so I'll highlight that. We've got a cosine value that's root 3 over 2 at pi over 6, but I actually notice that there's another one down here at 11 pi over 6. So this actually has two answers. So the x values here, if we're limiting our domain to 0 to 2 pi, would be pi over 6 or 11 pi over 6. Either one of those would be values or angles that would give us a cosine of root 3 over 2. And this sort of actually makes sense to me that there's more than, that there's two different answers for this, because we know that x is the cosine. So this is essentially thinking like on our unit circle that we're looking for a x value on our unit circle where we have root 3 over 2. So like x is root 3 over 2. And if we sort of think about what that would look like on this graph, it's almost like we're looking for a vertical line, and this vertical line has x is equal to the square root of 3 over 2, and we're trying to see where it intersects this circle, and it's going to intersect at these 2 points. And so it makes sense that there's one actually in our first quadrant and one in our fourth quadrant, because those are the 2 places where the x values would be the square root of 3 over 2. That is slightly different from sine values, which I guess I'll talk about a little bit later in this, which would have sort of these horizontal lines going across. But let's erase these lines that we've got for right here. We've got our solution, which is pi over 6 or 11 pi over 6. Okay, so we're getting some ideas now on like how to solve these problems. We've seen for sine of x is equal to 1. We've seen 2 cosine of x is equal to square root of 3. Now what about cosine of x is equal to 2? The question is, on our unit circle, or really it doesn't matter how many times we go around our unit circle, is there a place where the cosine of x, or the x value of these coordinates, is 2? The answer for that is no. There's no answer for this. Because we might notice that if we look at the x values, which are the cosines, the lowest value of those x values we could have is negative 1, and that goes all the way around until it gets to positive 1. And that again makes sense because we know a unit circle is a circle with radius 1. And so if we think about the range of cosine of x is only between negative 1 and 1. Those are the only values that we could have. We can't have something that gives us an output of 2. And so, this would be like undefined, or we could say there's no answer to this one. This one's sort of a trick because the range of cosine of x is negative 1 to 1. Similarly, the range of sine is from negative 1 to 1. If we look at the y values, that's the lowest y value up to the highest y value, going from negative 1 to 1 that we see here. So I will also put in parentheses sine 2. So it also has a range of negative 1 to 1. All right, what about number 4? 4 cosine squared of x is equal to 2. you know, we can just do order of operations. I would divide by 4 first. So this is cosine squared of x is equal to 2 over 4, which is 1/2. And if we take the square root of both sides, remember from earlier in this year, we said that when the squared is on the cosine, that expression is the same thing as cosine of x, this whole thing being squared, or cos x times cos x. Right? Those would be the same thing. Remember, we don't put the parenthesis, the exponent on the x, because we wouldn't know whether the whole thing was being multiplied by itself or just the x value. So this being on the cosine makes it clear that it's the whole thing being squared. So we need to take the square root of both sides. Cosine of x is going to be equal to the square root of 1/2. So the square root of 1/2. And here that's going to be equal to the square root of 1 divided by the square root of 2, or 1 over the square root of 2. And we know we can't leave our square radicals in the denominator. And so we multiply by root 2 over root 2. And so that's going to give us that this is equal to the square root of 2 over 2. Now, one thing I should mention, and we don't want to forget, notice here I took the square root of both sides. Since I took that square root of both sides, I do need to be careful to add a plus or minus. So this is plus or minus, this is plus or minus. And so there are two answers for this problem. One of those is positive square root of 2 over 2. The other is negative square root of 2 over 2. And those would be our answers for problem number 4. So if we took that, we could plug it into our equation. That would give us the correct answer for this. How would we write an expression for all solutions to sine of x is equal to negative square root of 3 over 2 from negative infinity to infinity? So we're being very clear in this problem that we're not talking about just the unit circle, right? Just the unit circle would be if we were talking about from 0 to 2 pi in terms of radians. This is telling us we could go around that unit circle as many times as we want. We can go forwards around it, we can go backwards around it. And so let's think about where, first off, on just our unit circle, that sine of x is equal to negative root 3 over 2. Sine, again, is our y value. If I'm looking for negative root 3 over 2, I'm not seeing any y values over here that are negative root 3 over 2. Oh, that's one right here at, looks like 4 pi over 3. So we've got that y value of negative root 3 over 2. And then, oh, it looks like we've got another one over here at 5 pi over 3. So those two values are ones, 4 pi over 3 and 5 pi over 3 would be angles that would work for this. So we're going to say x equals 4 pi over 3, or x equals 5 pi over 3. Now again, these are the only solutions that are on the unit circle. How would we represent other solutions? How would we represent, they said in this case, all solutions? Well, we recognize again that if we're on a unit circle, this may be a solution right here, right? 4 pi over 3. But if I went all the way around the circle again and added 2 pi, I would be back at this exact same spot. If I added 2 pi again, I'd be back at the same spot. In fact, I could add 2 pi a bunch of times, as many times as I want, and it's going to give me the exact same answer because we're going around the circle and ending up where we started, since 2 pi radians is a whole circle. So the way that we write that mathematically is that we say, well, we can take this 4 pi over 3 and we can either add or subtract. So I'm going to put a plus or minus 2 pi, I'm going to sort of put in parentheses, times n. And what this represents is this n value is essentially the number of times around the circle. What I'm saying here is I don't really even care how many times it is. You plug in some whole number value of n, and this is going to generate as many answers as you want. 4 pi over 3 plus or minus 2 pi times whatever your values of n is, assuming it's like an integer in this case. We can do that same idea here for the 5 pi over 3, because similarly we could go around the circle sort of as many times as we want, and really that's going to give us generate more answers as well. So notice sort of a difference in say number 4 versus number 5, right? Number 4 didn't specify that we were talking about negative infinity to infinity. We were sort of assuming that they're only talking about our unit circle. And so we have these two values for it. But if we wanted to find all of the solutions, we have this like extra expression that we're adding to the 2 that we found on the unit circle. So we found these on the unit circle, and then we're saying, okay, we can add a circle as many times as we want. We could subtract a circle as many times as we want for either one of these, and they're going to give us more answers. All right. Next, arcsine, arccosine, arctangent to solve equations using your calculator. Now, sometimes, and this is a limitation on the unit circle, but sometimes we have values, for example, like 0.43 that are not on the unit circle, right? I don't know any sign would be what our y values, so I'd be looking for places where y is equal to 0.43. Where is that on here? I got a half, root 2 over 2. I don't actually know. And in fact, none of these radical expressions, excuse me, none of these radical expressions would simplify to be exactly 0.43. So this is only, like the unit circle is only useful for these particular values and for these particular angles. And it's a lot of angles and it's a lot of values, but it's not all of them. So the question is, what do we do if we get something like this that's not on the unit circle? If I were to solve this, you know, I guess let me step aside and we can do a little bit of side work over here. If I were to give you the equation x squared is equal to 0.43, if I gave you x squared is equal to 0.43, and we wanted to solve for x, we know intuitively that what we would do here is we would take the square root of both sides, right? We would take the square root, and then we would say that, you know, we'd add that plus or minus. We'd say that x is equal to plus or minus the square root of 0.43, whatever that is. Why did we take a square root here? What was the reason? The reason for that is that we know that x squared and the square root of x are inverses. They're inverse functions. And what that means is that x squared and the square root of x, they cancel each other out when you have an equation, right? We know that if I had, 5 squared and the square root of that the squared and square root would cancel, that would just give us 5. We also know that if I took the square root of 5 and then I squared that would also be 5. So it's nice that we have these inverse functions that help us cancel out squareds, or we could square a square root to cancel that out. And we use that often, probably a lot in Algebra 2 and sometimes in AP Calculus as well. So the question is, what would cancel out this sign? Right now the x is inside of this sine function. How do we get that to go away? Well, in addition to our reciprocal trig functions, which we talked about back here, right, cosecant, secant, and cotangent, there are what are referred to as the inverse trig functions. So there are what's called the inverse trig functions. And technically, I'm sure there's inverse trig functions for all 6 of the basic trig functions, including those reciprocal ones. But generally, we normally only talk about what's called the arc sign. So it's the arc sign of x, the arc cosine, and the arc cotangent, or arctan for that. Now, for those of you who remember your inverse rules from last year, from Honors Algebra 2 and Algebra 2, you might remember that little -1 is a symbol that means inverse, right? If I'm talking about a function, right, f of x, the inverse function is often written with this little -1 here to represent that it is the inverse of that function. So these are little symbols that are telling us that we're actually talking not about sine, cosine, and tangent, but they're inverses for this. How does that work, like algebraically? Well, really what I'm going to do is I'm going to take the arc sine of both sides of this equation. the arcsine of both sides of this equation. Now, since these two are inverses of each other, arcsine and sine, they cancel each other out on that side of the equation, leaving me with just the x over here, which means that x is going to be equal to whatever the arcsine of 0.43 is. Now, at this point, again, my unit circle is of no help. We would need to use our calculator to find an estimate for that x value, and I would encourage you and again remind you that it is essential that your calculator is in radian mode. It must be in radian mode for AP Calculus. Otherwise, you're going to get incorrect answers if something like this came up, for example, on the free response of the AP exam. So if we do the arcsine, it actually shows up on your calculator above the sine symbol or the sine key. So if you take a look on your calculator and look at that sine button, you'll normally see the arcsine right above it. And so you can do second and sine to pull that up. But the arcsine of 0.43, if you test that out, should be about 0.444 if we're rounding to 3 decimal places. So that would give us a value that we could plug in to get sine for this. Now, we have these 3 inverse trig functions. Obviously, the arcsine is going to cancel sine out, right? That's why we use that up here. That's why I didn't use arc cosine or arctangent. Arcsine cancels sine. If you have a problem with cosine in it, then you could use arc cosine to cancel that out. And then arctan will cancel tans out in those problems. This is not something that comes up terribly often on the AP exam, but I do think it's like a useful thing to know that these have inverse functions. When we get later into derivative rules, there are actually rules that come into play talking about these types of trig functions. And so I'm glad we're doing a little bit of review, or it might even be an introduction to the fact that these trig functions exist and that they're used to cancel out equations that have sine and cosine and tangent in it. All right, let's go to the last bit for today, the Pythagorean identities. This graph should look familiar for those of us who watched the first video. We used this idea to sort of set up and figure out what the coordinates were going to be and to prove that the x value is the cosine and the y value is the sine. A reminder, right, for our unit circle, we know it's a unit circle because it starts at the origin, right? The center is at the origin, and that the radius of that circle is 1. That's why it's defined as a unit circle. So in this particular picture, we might notice that there's a line going from the center to the edge right here. So that means that that hypotenuse of that drawn right triangle is also 1. I'm going to draw that real big right here. And, as to scale as we can get. But here's our 1, and we know that if this is our coordinate here, if this is our xy, and this is our 0, 0, that to go right and then go up, I'd have to go right whatever the x value is from this coordinate right here, and then I'd have to go up whatever the y value is. So I'm going to call that x and y here. Now, one of the rules that we have for right triangle is the Pythagorean theorem, right? We know the Pythagorean theorem, and we know that it says a squared plus b squared is equal to c squared. We know that that's really only true for right triangles, and since we've got a right triangle, we're going to use that. I'm going to plug in what we've got here, and we're going to just see what we've got in terms of an expression. Specifically, our a value, I'm going to call, that's x, so x squared plus y squared is equal to 1 squared. Okay, well, so it's almost the same thing, but just with some different variables. Why is this useful? Where is this going? Well, if we think about our coordinate that we had up here, we said that the x in the coordinate was cosine of whatever our angle is. So let's say that's our angle. And we said that y was the sine of that whatever that angle is. So I'm going to substitute both of those in for this equation, and that actually tells us that cosine of theta squared plus sine of theta squared is equal to 1 squared, which is 1. Or I'm going to rewrite this a little bit more generally, but sine squared of theta plus cosine squared of theta is equal to 1. This is what's referred to as the Pythagorean identity. The Pythagorean identity. And it's one of 3 versions of this. But what does this say? It actually says that whatever our angle is, doesn't matter what the angle is, if you take sine squared of that angle plus the cosine squared of that angle, that's going to always equal 1. So for example, let's say that my angle is pi over 3. I know from the Pythagorean identity that even without doing any work, if I were to take sine squared of pi over 3 plus cosine squared of pi over 3, that it's going to simplify and just become 1. That's really nice. And that's true for all sorts of angles or sideline, or all sorts of angles, radians, degrees. As long as they're the same in both of these expressions and they're both being squared for that. That's really nice. And that comes up sometimes. It's useful in terms of simplifying problems. There are 2 other forms of this, which we're going to just quickly go into, and I'll show you where they come from. They both start off with this sine squared of theta plus cosine squared of theta is equal to 1. And the other one starts with the exact same thing. So I'm just going to get that set up. All right, well, on this first one, what we're going to do is we're going to actually divide the whole equation by sine. And actually, I'm going to divide by sine squared of theta. Let's see what happens. So if I divide the equation by sine squared of theta, that means that each part needs to get divided. So I'm dividing by sine squared of theta, I'm dividing by sine squared of theta, and I'm dividing by sine squared of theta. What do we have? Well, we have here that we have sine squared of theta over sine squared of theta. That's going to simplify and just become 1, plus cosine squared theta divided by sine squared of theta. If we think back to our reciprocal trig functions that we had here, we said that the tangent is the opposite over adjacent, or we said that tangent was sine over cosine, and we also said that cotangent was the reciprocal of that. So one thing we can actually add, which we didn't necessarily explicitly talk about up here, is that cotangent of theta is the cosine over the sine. Again, if we notice, like, hey, it's the reciprocal of that. And so in this case down here, since we've got a cosine squared divided by sine squared of theta, this is going to be the cotangent squared theta. Because, again, cosine over sine is cotangent, and those are both being squared, so that's going to simplify. This is going to be equal to 1 over sine squared of theta. If we think back to, again, our reciprocal trig functions up here, we said that 1 over sine is actually called cosecant. So this is the same thing as cosecant squared of theta. This is our second Pythagorean identity. So we've got one Pythagorean identity here, second Pythagorean identity here, and then what about our third one? The last one that we've got is, I'm going to imagine, not even imagine, we're going to divide this whole equation by cosine squared of theta. Every expression, each part of the equation needs to be divided by cosine squared. In this case, what's this going to become? Well, we have sine divided by cosine. Sine divided by cosine is what tangent is defined as. So this is actually tan squared of theta, plus cosine divided by cosine is 1, so that's going to be just itself, and that's equal to 1 over cosine squared of theta. Going back up and thinking about our reciprocal trig functions, 1 over cosine is actually secant, so that is secant squared theta. And this is our third and final Pythagorean identity. These three don't come up terribly often, but they are useful sometimes in terms of simplifying problems. I wanted you to be aware of what those identities were, and just that they exist and that they sometimes come up. Really, honestly, the most common one that comes up is this one, is this first one. I almost never see the other two, but they're useful just because they do occasionally come up. This is the one that we should definitely know and definitely be thinking about. If you've got something being squared, sine being squared, and cosine being squared, if I see a sine squared and a cosine squared in a problem, I'm thinking about Pythagorean identity all the way. Great. That's going to be it for today. That was our video. We went through a whole bunch of stuff in this one. We talked about reciprocal trig functions. We talked about using the unit circle to solve problems like sine of x is equal to 1. We introduced the arc sine, arc cosine, and arc tangent that help us cancel out as reciprocals. We talked about using your calculator to solve basic trig problems. And then we talked about Pythagorean identities. Have a great rest of your day. Hope that was useful. Take care.